Hello, I'm Brian from AirwaysAvionics.com. In this video, I'm going to talk about how the Glideslope portion of the Instrument Landing System, or ILS, works. The Glideslope is a radio navigational aid that provides aircraft on an instrument approach with vertical guidance down to the runway environment. The system consists of a ground-based transmitter and an airborne receiver. The transmitter is located on the airport property and operates in the UHF band between 328 and 335 MHz. The airborne receiver works in conjunction with the ILS localizer receiver. Frequencies are assigned in pairs so that when the aircraft tunes to the ILS localizer frequency, the associated glideslope frequency is automatically tuned. The transmitter antennas are located on a mast adjacent to the runway. There may be 2 or 3 antennas on the mast depending on the condition of the surrounding terrain. In areas with generally flat terrain, most systems will be the 2 antenna type. These are referred to as null reference systems. Systems in areas with sloping terrain or other discontinuities will use a 3 antenna system referred to as a capture effect system. Finally, in areas limited to with limited flat terrain, maybe there's dense population, mountains, drop-offs, or water, they'll use a system called an end-fire system. This is necessary because of the lack of a good reflecting ground surface. As a result, the end-fire system uses an entirely different antenna arrangement. Today I'm going to focus on the 2 antenna system. Depending on the heights of the antennas above the ground and each other, the angle of the resulting glideslope beam can be adjusted during installation to suit the particular runway location. Typically, the glideslope will point up from the touchdown point at approximately 3 degrees. The transmitted signal is a vertically polarized continuous wave AM modulated UHF signal. The 2 antennas each radiate slightly different signals. The upper antenna radiates the UHF carrier along with modulated sidebands, and the lower radiates only the sidebands. The CW frequencies used to modulate the carrier are 90 and 150 Hz. Thus, the sideband antenna broadcasts only the upconverted 90 and 150 Hz sidebands. The radiation pattern formed by these 2 antennas can be conceptualized as if there were a set of imaginary image or mirrored antennas radiating from inside the ground plane. However, the pattern is actually formed through spatial interference between the direct and reflected beams from the real antennas above the ground plane. The reflected beams are bouncing off the ground surface, so for the null reference system, it stands to reason that a flat and uniform ground plane is required. The direct and reflected beams are combined in free space and form areas where the sideband power is alternately constructive or destructive depending on the frequency. In this case, the area above the glideslope is an area of constructive 90 Hz sideband and destructive 150 Hz sideband interference. This results in higher 90 Hz sideband levels above the desired glideslope, and the area below the glideslope is an area of constructive 150 Hz and destructive 90 Hz. So the end result there is that there is an area of higher sideband power for 150 Hz below the desired glideslope. So it's higher 90 Hz above, higher 150 Hz below. The airborne glideslope receiver monitors and compares these levels. If the 90 Hz sideband power is greater, we know the aircraft is too high and you must descend. If the 150 Hz sideband power is greater, the aircraft is too low and you must stop descending or climb, as the case may be. So far, we can tell if we're above or below the glideslope, but we really don't know how far above or below we are. How does the system handle that? This is handled through something called difference in depth of modulation, or d.d.m for short. AM modulated signals such as your local AM radio station or glideslope reference channel have a signal metric known as depth of modulation. This is a number between 0 and 100% and is used to indicate how deeply the carrier amplitude is being modulated. Having a carrier with no AM modulation at all would result in a 0% depth of modulation value. Alternately, a carrier amplitude swing from peak amplitude to zero amplitude would result in 100% depth of modulation. So along the area of the desired glide slope, the sideband power is equal for 90 Hz and 150 Hz. Both tones are producing approximately a 40% depth of modulation. We talked a moment ago about the radiation patterns, areas of constructive and destructive sideband interference. These areas actually form gradients such that as they move further from the desired glide slope, the associated sideband's depth of modulation increases. This difference in depth of modulation signal drives the needle on the cockpit display to show the aircraft's position relative to the desired glide slope. As before, an increase in the depth of modulation of the 90 Hz signal means the needle will deflect to the low side of the glide slope. The aircraft is too high. An increase in the depth of modulation of the 150 Hz signal means the needle will deflect to the high side of the glide slope. Remember, we chase the needle on the glide slope, so if the needle is low, the glide slope is below us.